Chapter 7. The 18th Century. Section 1. Mathematical productivity in the 18th century concentrated on the calculus and its application to mechanics. The major figures can be arranged in a kind of pedigree to indicate their intellectual kinship. Leibniz, who lived from 1646 to 1716, the brothers Bernoulli, Jakob, who lived from 1654 to 1705, and Johann, who lived from 1667 to 1748, Euler, who lived from 1707 to 1783, Lagrange, who lived from 1707 to 1783, Lagrange and Range, who lived from 1700, and Hertine. Closely related to the work of these men was the activity of a group of French mathematicians, notably Clairaut, D'Alembert, and Maupertuis, who were again connected with the philosophers of the Enlightenment. To them must be added the Swiss mathematicians Lambert and Daniel Bernoulli. Scientific activity usually centered around academies, of which those at Paris, Berlin, and St. Petersburg were outstanding. University teaching played a minor role, or no role at all. It was a period in which some of the leading European countries were ruled by what have euphemistically been called enlightened despots. Frederick the Great, Catherine the Great, and also Louis XV and Louis XVI. Part of these despots' claim to glory was their delight in surrounding themselves with learned men. This delight was a type of intellectual snobbery, tempered by some understanding of the important role which natural science and applied mathematics were taking in improving manufacturing and increasing the efficiency of the military. It is said, for instance, that the excellence of the French Navy was due to the fact that in the construction of frigates and of ships of the line, the master shipbuilders were partly led by mathematical theory. Euler's works abound in applications to questions of importance to the army and navy. Astronomy continued to play its outstanding role as foster mother to mathematical research under royal and imperial protection. Section 2. Basel, in Switzerland. A free empire city since 1263, had long been a center of learning. In the days of Erasmus, its university was already a great center. The arts and sciences flourished in Basel, as in the cities of Holland, under the rule of a merchant patriciate. To this Basel patriciate belonged the merchant family of the Bernoullis, who had come from Antwerp in the previous century after that city had been conquered by the Spanish. From the late 17th century to the present time, this family in every generation has produced scientists. Indeed, it is difficult to find in the whole history of science a family with a more distinguished record. This record begins with two mathematicians, Jakob, also known as James or Jacques, and Johann, also known as John or Jean Bernoulli. Jakob studied theology, Johann studied medicine. But when Leibniz's papers in the Acta Eruditorum appeared, both men decided to become mathematicians. They became the first important pupils of Leibniz. In 1687, Jakob accepted the chair of mathematics at Basel University, where he taught until his death in 1705. In 1695, Johann became professor at Groningen taught. Upon his brother's death, he succeeded him in the chair at Basel, where he remained for 43 more years. Jakob began his correspondence with Leibniz in 1687. Then, in constant exchange of ideas with Leibniz, and with each other, often with bitter rivalry between them, the two brothers began to discover the treasures contained in Leibniz's pioneering venture. The list of their results is long and includes not only much of the material now contained in our elementary texts on differential and integral calculus, but also on the integration of many ordinary differential equations. Among Jakob's contributions are the use of polar coordinates, the study of the catenary, already discussed by Huygens and others, the lemniscate in 1694, and the logarithmic spiral. In 1690, he found the so-called isochrone, proposed by Leibniz in 1687, as the curve along which a body falls with uniform velocity. It appeared to be a semicubic parabola. Jakob also discussed isoperimetric figures in 1701, which led to a problem in the calculus of variations. The logarithmic spiral, which has a way of reproducing itself under various transformations. Its evolute is a logarithmic spiral, and so are both the pedal curve and the caustic with respect to the pole, was such a delight to Jakob that he willed that the curve be engraved on his tombstone with the inscription, Idem mutata resurgo, which means I shall arise the same though changed. Jakob died. Bernoulli was also one of the early students of the theory of probabilities, on which subject he wrote the Ars Conjectandi, published posthumously in 1713. In the first part of this book, Huygens' tract on games of chance is reprinted. The other parts deal with permutations and combinations and come to a climax in the Theorem of Bernoulli on binomial distributions. Bernoulli's numbers appear in this book in a discussion of Pascal's triangle. Section 3. Johann Bernoulli's work was closely related to that of his older brother, and it is not always easy to distinguish between the results of the two men. Johann is often considered the inventor of the calculus of variations because of his contribution to the problem of the brachistochrone. This is the curve of quickest descent for a mass point moving between 2 points in a gravitational field, a curve studied by Leibniz and the Bernoullis in 1697 and the following years. At this time, they found the equation of the geodesics on a surface. The answer to the problem of the brachistochrone is the cycloid. This curve also solves the problem of the tautochrone, the curve along which a mass point in a gravitational field reaches the lowest point in a time independent of its starting point. Huygens discovered this property of the cycloid and used it in constructing tautochronous pendulum clocks in 1673, in which the period is independent of the amplitude. Among the other Bernoullis who have influenced the course of mathematics are two sons of Johann, Nicolaus, and above all, Daniel. Nicolaus was called to St. Petersburg, founded only a few years before by Tsar Peter the Great. He stayed there for a short period. The problem in the theory of probability which he proposed from that city is known as the problem or, more dramatically, the paradox of St. Petersburg. This son of Johann died young, but the other, Daniel, lived to a ripe age. Until 1777 he was professor at the University of Basel. Daniel's prolific activity was mainly devoted to astronomy, physics, and hydrodynamics. His Hydrodynamica appeared in 1738, and one of its theorems on hydraulic pressure carries his name. In the same book, he established the kinetic theory of gases. With D'Alembert and Euler he studied the theory of the vibrating string, where his father and uncle developed the theory of ordinary differential equations. Daniel pioneered in partial differential equations. Section 4. Also from Basel came the most productive mathematician of the 18th century, if not of all time, Leonhard Euler. His father studied mathematics under Jakob Bernoulli, and Leonhard studied it under Johann Tautadadi. When in 1725, Johann's son Nicolaus traveled to St. Petersburg. Young Euler followed him, and stayed at the academy until 1741. From 1741 to 1766, Euler was at the Berlin Academy under the special tutelage of Frederick the Great. From 1766 to 1783, he was again at St. Petersburg, now under the aegis of the Empress Catherine. He married twice and had 13 children. The life of this 18th century academician was almost exclusively devoted to work in the different fields of pure and applied mathematics. Although he lost one eye in 1735 and the other eye in 1766, nothing could interrupt his enormous productivity. The blind Euler, aided by a phenomenal memory, continued to dictate his discoveries. During his life, 530 books and papers appeared. At his death he left many manuscripts which were published by the St. Petersburg Academy during the next 47 years. This brings the number of his works to 771. But research by Gustav Ennerstrom has completed the list to 886. Euler made significant contributions in every field of mathematics which existed in his day. He published his results not only in articles of varied length but also in an impressive number of large textbooks, which ordered and codified the material assembled during the ages. In several fields, Euler's presentation has been almost final. An example is our present trigonometry with its conception of trigonometric values as ratios and its useful notation, which dates from Euler's Introductio in Analysin Infinitorum in 1748. The tremendous prestige of his textbooks settled forever many moot questions of notation in algebra and calculus. Lagrange, Laplace, and Gauss knew and followed Euler in all their works. The Introduction of 1748 covers in its 2 volumes a wide variety of subjects. It contains an exposition of infinite series, including those for e to the x sine of x and cosine of x, and presents the relation e to the ix equals cosine x plus I sin x, already discovered by Johann Bernoulli and others in different forms. Curves and surfaces are so freely investigated with the aid of their equations that we may consider the introduction of the first text on analytic geometry. We may also find here an algebraic theory of elimination. To the most exciting parts of this book belong the chapter on the zeta function and its relation to the prime number theory, as well as the chapter on partition of numbers. Another great and rich textbook was Euler's Institutions Calculi Differentialis in 1755, Bach-Tuel, followed by 3 volumes of Institutions Calculi Integralis from 1768 to 1774. Here we find not only our elementary differential and integral calculus but also a theory of differential equations, Taylor's theorem with many applications, Euler's summation formula, and the Eulerian integrals t and b. The section on differential equations with its distinction between linear exact and homogeneous equations is still the model of our elementary texts on this subject. Euler's Mechanica, der Aristotle, Sive Motus Scientia Analytis, Exposita from 1736, was the first textbook in which Newton's dynamics of the mass point was developed with analytical methods. It was followed by the Theoria Motus Corporum Solidorum, So Rigidorum from 1765, in which the mechanics of solid bodies was similarly treated. This textbook contains the Eulerian equations for a body rotating about a point. The Vollständige Entgleitung zur Algebra from 1770, written in German and dictated to a servant because of Euler's blindness, has been the model of many later texts on algebra. It leads up to the theory of cubic and biquadratic equations and ends with a chapter on indeterminate equations, in which we find the proofs that x cubed plus y cubed equals z cubed is impossible for integers x, y, and z, when n equals 3 and n equals 4. In 1744, Euler's Methodus Inveniendi, Lineas Curvae, Maximi Minimae Proprietate Gaudentes was published. This was the first exposition of the calculus of variations. It contained Euler's equations, with many applications, including the discovery that catenoid and right helicoid are minimal surfaces. Many other results of Euler can be found in his smaller papers, which contain many a gem, little known even today. To the better-known discoveries belong the theorem connecting the number of vertices, edges and faces of a closed polyhedron, the line of Euler in the triangle, the curves of constant width which Euler called orbiform curves, and the constant of Euler gamma equals 0.577216. Several papers are devoted to mathematical recreations, like the 7 bridges of Königsberg and the knight's jump in chess. Euler's contributions to the theory of numbers alone would have given him a niche in the Hall of Fame. Among his discoveries in this field is the law of reciprocity for quadratic residues. A large amount of Euler's activity was devoted to astronomy, where the lunar theory, important both as a section of the three-body problem and in the solution of the problem of finding longitude, received his special attention. The Theoria Motus Planetarum et Cometarum from 1774 is a treatise on celestial mechanics. Related to this work was Euler's study of the attraction of ellipsoids in 1738. There are books by Euler on hydraulics, on ship construction, and on artillery. In 1769-71, there appeared 3 tomes of a dioptrica with a theory of the passage of rays through a system of lenses. In 1739 appeared his new theory of music, of which it has been said that it was too musical for mathematicians and too mathematical for musicians. Euler's philosophical exposition of the most important problems of natural science in his letters to a German princess from 1760 to 1761 remained a model of popularization. The enormous fertility of Euler has been a continuous source of surprise and admiration for everyone who has attempted to study his work. A task not so difficult as it seems, since Euler's Latin is very simple, and his notation is almost modern, or perhaps we should better say that our notation is almost Euler's. A long list can be made of the known discoveries for which Euler possesses priority, and another of ideas which are still worth elaborating. Great mathematicians have always appreciated their indebtedness to Euler. Read Euler. Laplace used to say to younger mathematicians, read Euler, he is the master of us all. And Gauss more ponderously expressed himself. The study of Euler's works will remain the best school for the different fields of mathematics, and nothing else can replace it. Riemann knew Euler's works well, and some of his most profound writings have an Eulerian touch. Publishers might do worse than offer translations of some of Euler's works, together with modern commentaries. Section 5. It is instructive to point out not only some of Euler's contributions to science but also some of his weaknesses. Infinite processes were still carelessly handled in the 18th century, and much of the work of the leading mathematicians of that period impresses us as wildly enthusiastic experimentation. There was experimentation with infinite series, with infinite products, with integration, with the use of symbols such as 0, infinity, and the square root of -1. If many of Euler's conclusions can be accepted today, there are others concerning which we have reservations. We accept. For instance, Euler's statement that the logarithm of n has an infinity of values which are all complex numbers, except when n is positive, when one of the values is real. Euler came to this conclusion in a letter to D'Alembert in 1747, who had claimed that the logarithm of -1 equals 0 doe. But we cannot always follow Euler when he writes that 1 minus 3 plus 5 minus 7, and so on, equals 0, or when he concludes from 1 over 1 plus 1 over 2 plus 1 over 3, and so on, and 1 over 1 squared plus 1 over 2 squared, and so on, that 1 plus 1 plus 1, and so on, equals -1 over 12. Yet we must be careful and not criticize Euler too hastily for his way of manipulating divergent series. He simply did not always use some of our present tests of convergence or divergence as a criterion for the validity of his series. Much of his supposedly indiscriminate work with series has been given a strictly rigorous sense by modern mathematicians. We cannot, however, be enthusiastic about Euler's way of basing the calculus on the introduction of zeros of different orders. An infinitesimally small quantity, wrote Euler in his differential calculus of 1755, is truly zero. A plus n dx equals a 2dx plus dx squared plus 1 equals dx, and a square root of dx plus cd dx equals a square root of dx equals. Therefore, there exist infinite orders of infinitely small quantities, which, though they all equal 0, still have to be well distinguished among themselves. If we look at their mutual relation, which is explained by a geometrical ratio, the whole question of the foundation of the calculus remained a subject of debate. And so did all questions relating to infinite processes. The mystical period in the foundation of the calculus, to use a term suggested by Karl Marx, itself provoked a mysticism which occasionally went far beyond that of the founding fathers. Guido Grandi, a priest and professor at Pisa known for his study of rosaces, which is r equals sine n theta, and other curves which resemble flowers, considered the formula 1 minus 1 plus 1, minus 1, and so on, equals 1 minus 0 plus 0, and so on, equals 0, as the symbol for creation from nothing. He obtained the result 1/2 by considering the case of a father who bequeaths a gem to his 2 sons, who each may keep the bauble 1 year in alternation. Then belongs to each son for 1/2. Euler's foundation of the calculus may have had its weakness, but he expressed his point of view without vagueness. D'Alembert, in some articles of the Encyclopedic, attempted to find this foundation by other means. Newton had used the term prime and ultimate ratio for the fluxion, as the first or last ratio of 2 quantities just springing into being. D'Alembert replaced this notion by the conception of a limit. One quantity he called the limit of another when the second approaches the first nearer than by any given quantity. The differentiation of equations consists simply in finding the limits of the ratio of finite differences of 2 variables included in the equation. This was a great step ahead, as was D'Alembert's conception of infinites of different orders. However, his contemporaries were not easily convinced of the importance of the new step, and when D'Alembert said that the secant becomes the tangent when the 2 points of intersection are 1, it was felt that he had not overcome the difficulties inherent in Zeno's paradoxes. After all, does a variable quantity reach its limit, or does it never reach it? We have already referred to Bishop Berkeley's Criticism of Newton's Fluxions. George Berkeley, Dean of Derry in 1724, Bishop of Cloyne in South Ireland in 1734, and from 1729 to 1731, a resident of Newport, Rhode Island, is primarily known for his extreme idealism, which is to be perceived. Is to be perceived. He resented the support which Newtonian science gave to materialism, and he attacked the theory of fluxions in the Analyst in 1734. He derided the infinitesimals as ghosts of departed quantities. If x receives an increment o, then the increment of x to the nth power, divided by o, is obtained by supposing o different from 0. The fluxion of x to the nth power, however, is obtained by taking o as equal to 0, when the hypothesis is suddenly shifted since o was supposed to be different from 0. This was the manifest sophism, which Berkeley discovered in the calculus, and he believed that its correct results were obtained by a compensation of errors. Fluxions were logically unaccountable, but he who can digest a second or third fluxion. A second or third difference, Berkeley exclaimed to the infidel mathematician whom he addressed, Halley need not, methinks, be squeamish about any point in divinity. It has not been the only case in which a critical difficulty in a science has been used to strengthen an idealist philosophy. John Landon, a self-taught British mathematician whose name is preserved in the theory of elliptic integrals, tried to overcome the basic difficulties in the calculus in his own way. In the residual analysis in 1764, he met Berkeley's criticism by avoiding infinitesimals altogether. The derivative of x cubed, for instance, was found by changing x into x plus x1, after which x cubed becomes x cubed plus 3x squared x1 plus 3 x1 squared plus x1 cubed, and this divided by x1 becomes 3x1, becomes 3x squared plus 3x1 plus x1 squared. Since this procedure involves infinite series when the functions are more complicated, Landon's method has some affinity to the later, algebraic method of Lagrange. Section 6. Although Euler was incontestably the leading mathematician of this period, France continued to produce work of great originality. Here, more than in any other country, mathematics was conceived as the science which was to bring Newton's theory to greater perfection. The theory of universal gravitation had great attraction for the philosophers of the Enlightenment, who used it as a weapon in their struggle against the remnants of feudalism. The Catholic Church had placed Descartes on the index in 1664. But, by 1700, his theories had become fashionable even in conservative circles. The question of Newtonianism versus Cartesianism became for a while a topic of the greatest interest, not only in learned circles, but also in the salons. Voltaire's Letters sur l'Anglais from 1734 did much to introduce Newton to the French reading public. Voltaire's friend Madame du Châtelet even translated the Principia into French in 1759. A particular point of contention between the two schools was the figure of the Earth. In the cosmogony favored by the Cartesians, the Earth elongated at the poles. Newton's theory required that it be flattened. The Cartesian astronomers Cassini, Jean-Dominique, the father, and Jacques, the son, the father known in geometry because of Cassini's oval in 1680, had measured an arc of the meridian in France between 1717 and 1720 and vindicated the Cartesian conclusion. A controversy arose in which many mathematicians participated. An expedition was sent in 1735 to Peru. Followed in 1736–37 by one under the direction of Pierre de Maupertuis to the Tornea in Sweden among the Lapps in order to measure a degree of longitude. The result of both expeditions was a triumph for Newton's theory, as well as for Maupertuis himself, the now famous Grand Aplatisseur, which means great flattener, became president of the Berlin Academy and basked for many years in the sun of his fame at the court of Frederick the Great. This lasted until 1750, when he entered into a spirited controversy with the Swiss mathematician Samuel Koenig concerning the principle of least action in mechanics, perhaps already indicated by Leibniz. Maupertuis was looking, as Fermat had done before and Einstein has done after him, for some general principle by which the laws of the universe could be unified. Maupertuis's formulation was not clear, but he defined as his action the quantity m times v times s, where m equals mass, v equals velocity, and s equals distance. He combined with it a proof of the existence of God. The controversy was brought to a climax when Voltaire lampooned the unhappy president in the diatribe Du Docteur Akakia, Médecin du Pape, in 1752. By 1752. Neither the king's support nor Euler's defense could bring succor to Maupertuis' sunken spirits, and the deflated mathematician died not long afterwards in Basel in the home of the Bernoullis. Euler restated the principle of least action in the form that the integral of mvds must be a minimum. Moreover, he did not indulge in Maupertuis' metaphysics. This placed the principle on a sound basis, where it was used by Lagrange and later by Hamilton. The use of the Hamiltonian in modern mathematical physics illustrates the fundamental character of Euler's contribution to the Maupertuis-Koenig controversy. Among the mathematicians who went with Maupertuis to Lapland was Alexis Claude Clairaut, datado Clairaut, at 18 years of age, had published the Recherches sur les courbes, a double courbier, in 1731, a first attempt to deal with the analytical and differential geometry of space curves. Upon his return from Lapland, Clairaut published his Théorie de la figure de la Terre in 1743, a standard work on the equilibrium of fluids and the attraction of ellipsoids of revolution. Laplace could only improve on it in minor details. Among its many results is the condition that a differential m dx plus n dy be exact. This book was followed by the Theorie de la Lune in 1752, which added material to Euler's theory of the moon's motion and the problem of three bodies in general. Clairaut also contributed to the theory of line integrals and of differential equations. One of the types which he considered is known as Clairaut's equation. It offered one of the first known examples of a singular solution. To Clairaut is also due the theorem that for a function of x and y, the values of the second derivative of y with respect to x and y with respect to x are equal. Section 7. The intellectual opposition to the ancient regime centered after 1750 around the famous Encyclopédie d'Arts de Wararts, 28 volumes published from 1751 to 1772. The editor was Denis Diderot, under whose leadership the encyclopedia presented a detailed philosophy of the Enlightenment. Diderot's knowledge of mathematics was not inconsiderable, but the leading mathematician of the encyclopedists was Jean-Laurent d'Alembert, the natural son of an aristocratic lady, left as a foundling near the church of Saint-Jean-Laurent in Paris. His early brilliance facilitated his career. In 1754 he became Secretary Perpetual of the French Academy, and as such the most influential man of science in France. In 1743 appeared his Traité de dynamique, which contains the method of reducing the dynamics of solid bodies to statics, known as D'Alembert's principle. Diderot's early brilliance facilitated his career. In 1754, he became the perpetual secretary of the French Academy, and as such, the most influential man of science in France. In 1743, his Traité de dynamique appeared, containing the method of reducing the dynamics of solid bodies to statics, known as D'Alembert's principle. He continued to write on many applied subjects, especially on hydrodynamics, aerodynamics, and the three-body problem. In 1747, his theory of vibrating strings appeared, making him, together with Daniel Bernoulli, the founder of the theory of partial differential equations, where D'Alembert and Euler solved the equation for vibrating strings by means of the expression of a continuous function. Bernoulli solved it by means of a trigonometric series. There remained grave doubts concerning the nature of this solution. D'Alembert believed that the initial form of the string could only be given by a single analytical expression, while Euler thought that any continuous curve would do. Bernoulli believed, contrary to Euler, that his series solution was perfectly general. The full explanation of the problem had to wait until 1824, when Fourier removed the doubts concerning the validity of a trigonometric series as the representation of any function. D'Alembert was a facile writer on many subjects, including even fundamental questions in mathematics. We mentioned his introduction of the limit conception. The fundamental theorem in algebra is sometimes called D'Alembert's theorem because of his attempt at proof in 1746, and D'Alembert's paradox in the theory of probability, shows that he also thought about the foundations of this theory, if not always very successfully. The theory of probabilities made rapid advances in this period, mainly by further elaboration of the ideas of Fermat, Pascal, and Huygens. The Ars Conjectionandi was followed by several other texts, among them the Doctrine of Chances in 1716, written by Abraham de Moivre, a French Huguenot who settled in London after the revocation of the Edict of Nantes in 1685, and earned a living by private tutoring. De Moivre's name is attached to a theorem in trigonometry, which, in its present form, cosine phi plus I sine phi, to the power of n equals cosine of n phi, plus I sine of n phi appears first in Euler's Introductio, in a paper published in 1733. He derived the normal probability function as an approximation to the binomial law, and a formula equivalent to that of Stirling. James Stirling, an English mathematician of the Newtonian school, published his series in 1730. The many lotteries and insurance companies which were organized in this period interested many mathematicians, including Euler, in the theory of probabilities. It led to attempts to apply the doctrine of chances to new fields. Georges-Louis Leclerc, Tade, Comte de Buffon, director of the Paris Jardin du Roi, who is noted as the author of A Natural History, in 36 delightful volumes, and the famous Discourse on Style in 1753. Le Style est de l'homme même, introduced in 1777, the first example of a geometrical probability. This was the so-called needle problem, which has appealed to the imagination of many people, because it allows the experimental determination of pi by throwing a needle on a plane covered with parallel and equidistant lines, and counting the number of times the needle hits a line. To this period belongs also the attempts to apply the theory of probability to man's judgment. For instance, by computing the chance that a tribunal can arrive at a true verdict if to each of the different witnesses and jurymen a number can be given expressing the chance that he will speak or understand the truth. This curious probability of judgments, with its distinct flavor of Enlightenment philosophy, was prominent in the work of the Marquis de Condorcet. It reappeared in Laplace and even in Poisson in 1837. Section 8. De Moivre, Stirling, and Landon were good representatives of English 18th century mathematicians. We must report on a few more, although none of them reached the height of their continental colleagues. The tradition of the venerated Newton rested heavily upon English science, and the clumsiness of his notation, as compared to that of Leibniz, made progress difficult. There were deep-lying social reasons why English mathematicians refused to be emancipated from Newtonian fluxional methods. England was in constant commercial wars with France and developed a feeling of intellectual superiority, which was fostered not only by its victories in war and trade, but also by the admiration in which the continental philosophers held its political system. England became the victim of its own supposed excellence. An analogy exists between the mathematics of 18th century England and of late Alexandrian antiquity. In both cases progress was technically impeded by an inadequate notation. But reasons for the self-satisfaction of the mathematicians were of a deeper-lying social nature. The leading English, or rather English-speaking, mathematician of this period was Colin Maclaurin, professor at the University of Edinburgh, a disciple of Newton with whom he was personally acquainted. His study and extension of fluxional methods, of curves of second and higher order, and of the attraction of ellipsoids run parallel with contemporary efforts of Clairaut and Euler. Several of Maclaurin's theorems occupy a place in our theory of plane curves and our projective geometry. In his Geometria Organica in 1720, we find the observation known as Cramer's paradox, that a curve of the nth order is not always determined by 1/2 n times n plus 3 points, so that 9 points may not uniquely determine a cubic while 10 would be too many. Here we also find cinematical methods to describe plane curves of different degrees. Maclaurin's Treatise of Fluxions, 2 volumes published in 1742 and written to defend Newton against Berkeley, is difficult to read because of the antiquated geometrical language, which is in sharp contrast with the ease of Euler's writing. Maclaurin used to obtain Archimedean rigor. The book contains Maclaurin's investigations on the attraction of ellipsoids of revolution and his theorem that two such ellipsoids, if they are confocal, attract a particle on the axis, or in the equator with forces proportional to their volumes. In this treatise, Maclaurin also deals with the famous series of Maclaurin. This series, however, was no new discovery, since it had appeared in the Methodus Incrementorum in 1715, written by Brooke Taylor, for a while Secretary of the Royal Society. Maclaurin fully acknowledged his debt to Taylor. The series of Taylor is now always given in Lagrange's notation. F of x plus h equals f of x plus h f prime of x plus h squared over 2 factorial f double prime of x plus, and so on. Taylor explicitly mentions the series for h equals 0 dot, which many college texts still insist on naming Maclaurin's series. Taylor's derivation did not include convergence considerations, but Maclaurin made a beginning with such considerations. He even had the so-called integral test for infinite series. The full importance of Taylor's series was not recognized until Euler applied it in his differential calculus in 1755. Lagrange supplied it with the remainder, and used it as the foundation of his theory of functions. Taylor himself used his series for the integration of some differential equations. He also began the study of the vibrating string, which was taken up later by D'Alembert and others. Section 9. Joseph Louis Lagrange was born in Turin of Italian-French ancestry. At 19 years of age, he became professor of mathematics in the Artillery School of Turin in 1755. In 1766, when Euler left Berlin for St. Petersburg, Frederick the Great invited Lagrange to come to Berlin, accompanying his invitation with a modest message which said that it is necessary that the greatest geometer of Europe should live near the greatest of kings. Lagrange stayed at Berlin until the death of Frederick in 1786, after which he went to Paris. During the Revolution he assisted in reforming weights and measures. Later he became professor, first at the École Normale in 1795, then at the École Polytechnique in 1797. To Lagrange's earliest works belong his contributions to the calculus of variations. Euler's memoir on this subject had appeared in 1755. Lagrange observed that Euler's method had not all the simplicity which is desirable in a subject of pure analysis. The result was Lagrange's purely analytical calculus of variations in 1760 to 1761, which is not only full of original discoveries, but also has the historical material well arranged and assimilated, something quite typical of all Lagrange work. Lagrange immediately applied his theory to problems of dynamics, in which he made full use of Euler's formulation of the principle of least action, the result of the lamentable Akakia episode. Many of the essential ideas of the Mécanique analytique thus date back to Lagrange's Turin days. He also contributed to one of the standard problems of his day, the theory of the moon, important not only for its own sake, but for the solution of the problem of finding longitude. Lagrange gave the first particular solutions of the three-body problem. The theorem of Lagrange states that it is possible to start three finite bodies in such a manner that their orbits are similar ellipses all described in the same time in 1772. In 1767, his memoir, On the Resolution of Numerical Equations, appeared, in which he presented methods of separating the real roots of an algebraic equation, and of approximating them by means of continued fractions. This was followed in 1770 by the Reflections on the Resolution of Algebraic Equations, which dealt with the fundamental question of why the methods useful to solve equations of degree less than or equal to 4 are not successful for degrees greater than 4. This led Lagrange to rational functions of the roots and their behavior under the permutations of the roots. The procedure which not only stimulated Ruffini and Abel in their work on the case degrees greater than 4, but also led Galois to his theory of groups. Lagrange also made progress in the theory of numbers when he investigated quadratic residues, and proved, among many other theorems, that every integer is the sum of 4 or fewer squares. Lagrange devoted the second part of his life to the composition of his great works, Mécanique analytique in 1788, Theory of Analytic Functions in 1797, and its sequel, Lessons on the Calculus of Functions in 1801. The two books on functions were an attempt to give a solid foundation to the calculus by reducing it to algebra. Reducing it to algebra. Lagrange rejected the theory of limits as indicated by Newton and formulated by D'Alembert. He could not well understand what happened when the ratio of delta y over delta x reaches its limit. In the words of Lazare Carnot, the organizer of victory in the French Revolution who also worried about Newton's method of infinitesimals. That method has the great inconvenience of considering quantities in the state in which they cease, so to speak, to be quantities, for though we can always well conceive the ratio of two quantities, as long as they remain finite, that ratio offers to the mind no clear and precise idea, as soon as its terms become, the one and the other, nothing at the same time. Lagrange's method was different from that of his predecessors. He started with Taylor's series, which he derived with their remainder, showing in a rather naive way that any function f of x could be developed in such a series with the aid of a purely algebraic process. Then, the derivatives f prime of x, f double prime of x, etc., were defined as the coefficients 1, 2, 3, and so on in the Taylor expansion of f of x plus h in terms of h. The notation f of x go. F prime of x is due to Lagrange. Though this algebraic method of founding the calculus turned out to be unsatisfactory, and though Lagrange gave insufficient attention to the convergence of the series, the abstract treatment of a function was a considerable step ahead. Here appeared a first theory of functions of a real variable, with applications to a large variety of problems in algebra and geometry. Lagrange's Mécanique analytique is perhaps his most valuable work, and still amply repays careful study. In this book, which appeared 100 years after Newton's Principia, the full power of the newly developed analysis was applied to the mechanics of points and of rigid bodies. The results of Euler, D'Alembert, and the other mathematicians of the 18th century were assimilated and further developed from a consistent point of view. Full use of Lagrange's own calculus of variations made the unification of the varied principles of statistics and dynamics possible in statistics by the use of the principle of virtual velocities, in dynamics by the use of D'Alembert's principle. This led naturally to generalized coordinates and to the equation of motion in their Lagrangian form, d by dt partial of t with respect to partial of q sub I equals partial of q with respect to partial of q sub I y. Newton's geometrical approach was now fully discarded. Lagrange's book was a triumph of pure analysis. The author went so far as to stress in the preface, "On ne trouvera point de figures dans cet ouvrage, seulement des opérations algébriques." It characterized Lagrange as the first true analyst. Section 10. With Pierre-Simon Laplace we reach the last of the leading 18th century mathematicians. The son of a small Normandy proprietor, he attended classes at Beaumont and Caen, and through the aid of D'Alembert became professor of mathematics at the Military School of Paris. He had several other teaching and administrative positions, and took part during the Revolution in the organization of the École Normale, as well as the École Polytechnique. Napoleon bestowed many honors upon him, but so did Louis XVIII. In contrast to Monge and Carnot, Laplace easily shifted his political allegiances, and with it all was somewhat of a snob. But this easy conscience enabled him to continue his purely mathematical activity, despite all political changes in France. The two great works of Laplace which unify not only his own investigations, but all previous work in their respective subjects, are Theory of Analytic Probabilities in 1812, and Celestial Mechanics in 5 volumes from 1799 to 1825. Both monumental works were prefaced by extensive expositions in non-technical terms. The Philosophical Essay on Probabilities in 1814, an exposition of the system of the world in 1796. This exposition contains the nebular hypothesis, independently proposed by Kant in 1755, and even before Kant by Swedenborg in 1734. The Celestial Mechanics was the culmination of the work of Newton, Clairaut, D'Alembert, Euler, Lagrange, and Laplace on the figure of the Earth, the theory of the Moon, the three-body problem, and the perturbations of the planets, leading up to the momentous problem of the stability of the solar system. The name Laplace's equation, which is the second derivative of v with respect to x, plus the second derivative of y with respect to y, plus the second derivative of v with respect to z equals 0, reminds us that potential theory is part of the celestial mechanics. The equation itself already had been found by Euler in 1752, when he derived some of the principal equations of hydrodynamics. Around this 5-tome opus cluster many anecdotes, well known as Laplace's supposed answer to Napoleon, who tried to tease him by the remark that God was not mentioned in his book. Sire, je n'avais pas besoin de cette hypothèse. And Nathaniel Bowditch of Boston, who translated 4 volumes of Laplace's work into English, has remarked, I never came across one of Laplace's, thus it plainly appears without feeling sure that I have hours of hard work before me to fill up the chasm and find out and show how it plainly appears. Hamilton's mathematical career began by finding a mistake in Laplace's celestial mechanics. Green, reading Laplace, received the idea of a mathematical theory of electricity. The philosophical essay on probabilities is a very readable introduction to the theory of probabilities. It contains Laplace's negative definition of probabilities by postulating equally likely events. The theory of chance consists in the reduction of all events of the same kind to a certain number of equally likely cases, that are cases such we are equally undecided about their existence, and to determine the number of cases which are favorable to the event of which we seek the probability. Questions concerning probability appear, according to Laplace, because we are partly ignorant and partly knowing. This led Laplace to his famous statement which summarizes the 18th century interpretation of mechanical materialism, an intelligence which, for a given instant, knew all the forces by which nature is animated and the respective position of the beings which compose it, and which besides was large enough to submit these data to analysis, would embrace in the same formula the motions of the motions of the largest bodies of the universe and those of the lightest atom. Nothing would be uncertain to it, and the future as well as the past would be present to its eyes. Human mind offers a feeble sketch of this intelligence in the perfection which it has been able to give to astronomy. The standard text itself is so full of material that many later discoveries in the theory of probabilities can already be found in Laplace. The stately tome contains an extensive discussion of games of chance and of geometrical probabilities, of Bernoulli's theorem and of its relation to the normal integral, and of the theory of least squares invented by Legendre. The leading idea is the use of the generating functions, of which Laplace shows the power for the solution of difference equations. It is here that the Laplace transform is introduced, which later became the key to the Heaviside operational calculus. Laplace also rescued from oblivion and reformulated a theory sketched by Thomas Bayes, an obscure English clergyman, which was posthumously published in 1763-64. This theory became known as the theory of inverse probabilities. Section 11. It is a curious fact that toward the end of the century, some of the leading mathematicians expressed the feeling that the field of mathematics was somehow exhausted. The laborious efforts of Euler, Lagrange, D'Alembert, and others had already led to the most important theorems. The great standard texts had placed them, or would soon place them, in their proper setting. The few mathematicians of the next generation would only find minor problems to solve. Does it not seem to you that the sublime geometry tends to become a little decadent? Wrote Lagrange to D'Alembert in 1772. She has no other support than you and Mr. Euler. Lagrange even discontinued working in mathematics for a while. D'Alembert had little hope to give. Arago, in his eulogy of Laplace in 1842, later expressed a sentiment which may help us to understand this feeling. 5 geometers, Clairaut, Euler, D'Alembert, Lagrange, and Laplace, shared between them the world of which Newton had revealed the existence. They explored it in all directions, penetrated into regions believed inaccessible, pointed out countless phenomena in those regions which observation had not yet detected, and finally, and herein lies their imperishable glory, they brought within the domain of a single principle, a unique law, all that is most subtle and mysterious in the motions of the celestial bodies. Geometry also had the boldness to dispose of the future. When the centuries unroll themselves, they will scrupulously ratify the decisions of science. Wow. Arago's oratory points to the main source of this fin de siècle pessimism, which consisted of the tendency to identify the progress of mathematics too much with that of mechanics and astronomy. From the time of ancient Babylon until that of Euler and Laplace, astronomy had guided and inspired the most sublime discoveries in mathematics. Now this development seemed to have reached its climax. However, a new generation, inspired by the new perspectives opened by the French Revolution and the flowering of the natural sciences, was to show how unfounded this pessimism was. This great new impulse came only in part from France. It also came, as often in the history of civilization, from the periphery of the political and economical centers, in this case, from Gauss, in Göttingen.